Hi everyone, we are back and we are on our last problem, our phase diagram. So let's fill out all the sections of the phase diagram. So we have a solid phase here that also looks like it goes through another solid phase. Basically a little transition here, but I think we'll just call this a full solid here. So anyways, this is going to be this solid plus this solid. This, I think we actually have to add a little bit. We're going to call this actually a gamma phase. We'll kind of put that in there. But anyways, let's go ahead and we will examine that a little bit. So, but anyways, that's going to be this phase plus this phase. This is going to be this phase plus this phase. This is going to be this phase plus this phase. This is going to be this phase right here. Actually, this phase plus this phase, that's a tricky one. This phase plus this phase plus this phase, liquid plus this phase, liquid plus this phase right here. This is going to be this plus this. This is going to be liquid plus this. This is going to be this plus this plus this. And this is going to be finally this plus this. So nasty, nice and messy, but we've got it. All right. Where are all the congruent melting points? Here and here. That's it. There's just two of them on this one. So two congruent melting points. I really don't see another particular phase unless you say maybe here, but that's a tough one. I would call that a congruent melting point there. So that can definitely be one of those. Excellent. What about, so those are congruent melting points. What are some of our invariant points? So this is a eutectoid because we are going to go from a solid to a two-phase solid region here. Excellent. What about, this is just a solid to another solid. What about here? Single solid to a two-phase solid. That's another eutectoid. Eutectic right here. I don't really see the two-phase solid region here. Here we have a peritectoid, liquid plus solid. Actually, this is not going to be peritectic, excuse me, because we're going from liquid to solid and then a two-phase region here, so it's not a pure phase. This will be a peritectoid. So we're doing sigma plus V to another, so two-phase solid region to a single-phase solid region, that's a peritectoid. This is another eutectoid, solid to another two-phase solid region here. Fantastic. I'm trying to see if we have any peritectics, but I do not believe so. And I think that those are all of our invariant points that we have in this particular system. So fantastic. All right. So let's go ahead. Good. All right. Consider a composition of 80% vanadium and 1200. So something 80% vanadium. So we're basically right here. What are the phases that exist? It's going to be, the phases are V and sigma. What are the components in this system? So the components are V and cobalt. Name explicitly. What is the composition fraction of each material? So composition that's in my vanadium phase will be, if I'm looking at this temperature approximately here. So if I go down here, let's just call that component that's in sigma is going to be, I'm going to call that 68. And then I'm going to say here, I'm going to call this, I'm going to call it 88. And then the fraction that's in my V phase will be equal to 88 minus 68. And then it's going to run across to the other side. So it is going to be 80 minus 68. Fraction that's going to be in my sigma, same denominator, 88 minus 68. And then it's going to be run to the other side. So that'll be 88 minus 80. And there we go. We've got it. Fantastic. Relate the chemical potentials. Chemical potential of my V phase is going to be equal to my chemical potential of my sigma phase. What are the degrees of freedom at this composition? So my degrees of freedom plus phases equals C plus 1. Components are 2. Phases are 2. Cancel, cancel. Degrees of freedom is 1. Makes sense. And then finally, draw the free energy curves at 1400 C. So let's go ahead and let's cancel this out. Good. Good. All right. 1400. So if we go here, so we're probably, yeah, just below. I'm going to actually, let's zoom in a little bit to make it a little bit easier on ourselves. Because basically we know we're going to go here through these two, below, and in here. So we're going to be drawing something that looks like this. G composition. So I cross through 1 here, 2, 3, 4 lines, 3, 4, 5, and then 6. I should have made that bigger, but we'll work with it. So first we are alpha phase, then we are alpha plus liquid, and then we are just liquid, and then we are liquid plus sigma, and then we are then we are just sigma, and then we are sigma plus V, and then we are just V. So I'm going to get some, oops, excuse me. Let's open that up. Drop this down. Come on, come down. Ah! What's the matter with you? Okay, here we go. We're going to just zoom this out a little bit. I'm going to call this, I'm going to keep this red here. So I need, actually, but I'm going to change this color now. I need my common tangents in my two-phase region. So I'm going to have a common tangent here. I'm going to have another common tangent here. And I'm going to have another common tangent here. So I'm going to keep this red as my alpha. So my alpha phase is going to just be hanging out. It's going to touch here, and then it's just going to disappear. My liquid is going to be this blue. So that's my liquid. The liquid, and that red should touch. So just to kind of make it a little bit clearer. It needs to touch here. You get the picture. My liquid is going to come here, touch, hang out, touch, and then it disappears. I'm going to call this is my sigma. So that's going to be hanging out, doing nothing, touching here, lowest free energy, and then it has to touch here as well, and then it disappears. And then finally, my V is going to be this, hanging out, doesn't really do anything, touches here, and then just hangs out. And there we go. That's our free energy curves. So we'll see you on the next exam. Thanks. Bye.